What quantum computers just proved about reality is terrifying. In October 2019, a machine completed a calculation in only 200 seconds. That same calculation, if given to the most powerful classical supercomputer on Earth, would still be running 10,000 years from now. Not 10 hours, not 10 months, 10,000 years. Your great-great-grandchildren's great-great-grandchildren would never live long enough to see the final answer. But the most disturbing part was not just the speed. The most disturbing part was this. No one can fully explain where the computation actually happened. Not Google, not IBM, not even the physicists who built the machine. There is one theory that seems to explain it. A physicist named David Deutsch proposed it back in 1985, and for decades, most people ignored him, until the hardware started doing exactly what his theory suggested it might do. If you are new here, hit the like button and subscribe to Cosmos Room channel. Pour yourself something warm, settle in, and get comfortable, because tonight we are going deep into what these machines really mean. We are going to talk about why the computation happening inside them may be far stranger than most people are willing to say out loud, and why the universe itself may have left us a clue in the one place almost everyone forgot to look. Now let's begin. Part 1. The result that broke reality. There is a machine sitting inside a laboratory in Santa Barbara, California. This machine completed a calculation in 200 seconds. The most powerful classical supercomputer on Earth would need around 10,000 years to finish that same task. Let that sink in for a moment. Not 10 years, not 100 years. 10,000 years. That is longer than all of recorded human civilization. From the earliest Sumerian clay tablets to the smartphone sitting in your hand, all of that history compressed into the time it takes to soft boil an egg. The team behind this machine was Google's quantum hardware division. They published their results in October 2019, and when they released that paper into the scientific world, it landed like a stone dropped into still water. The ripples are still moving. The processor was called Sycamore. It had 53 superconducting qubits. That number may sound small at first, almost ordinary, but it only sounds small until you understand what each qubit is actually doing. And we will get to that. The task Sycamore performed was called random circuit sampling. That means it executed a series of quantum logic operations chosen at random, then measured the output. At first, that might sound abstract. It might sound like a benchmark designed only for scientists, not a real-world application. And in one sense, that is exactly what it was. But benchmarks matter. Benchmarks tell you what a system is capable of. And what Sycamore showed it was capable of should not have been possible in any ordinary classical sense. Now, to be fair, IBM challenged Google's claim almost immediately. IBM's engineers looked at Google's 10,000-year estimate and said, no, with optimized classical algorithms and enough hard drive storage, this same circuit could probably be simulated in around 2.5 days. And they were not completely wrong. The debate between Google and IBM after that paper was one of the most fascinating moments in recent physics history. Two groups of brilliant people were basically arguing about how impossible the impossible thing really was. But here is the part both sides quietly agreed on. The gap was real. IBM was not saying classical computers were equal to quantum computers at this task. They were arguing about the size of the gap, not whether the gap existed, and the existence of that gap is the real story. Because what Google demonstrated for the first time was a machine performing a computation for which there was no efficient classical explanation, not a slow classical explanation that could simply be accelerated, not an approximate classical simulation that could just be refined, but a real measurable case where a quantum processor did something that classical physics, classical matter, and classical rules could not practically reproduce. The machine worked in a way that our conventional understanding of the universe should not fully allow. Then came Google Willow, announced in December 2024. And if Sycamore cracked the wall, Willow punched straight through it. Willow demonstrated something the entire field of quantum computing had been chasing for 3 decades: scalable quantum error correction. More specifically, it showed that when you increase the number of physical qubits used to encode a single logical qubit, the error rate does not stay the same. It does not increase, it drops exponentially. In other words, the more components you add to the system, the more stable the system becomes. Stop for a second and think about what that means in normal engineering. Every system you have ever seen in life behaves the opposite way. When you add more components, you usually add more possible points of failure. A car has more parts than a bicycle, so it can break in more ways. A city power grid has more failure modes than a single generator. A human body has far more ways to malfunction than one cell. That is not a flaw in design. That is entropy. That is the second law of thermodynamics, showing itself through every technology humans have ever built. More complexity usually means more fragility. That is the rule. Willow broke the rule. Below a certain physical error rate, what physicists call the fault tolerance threshold, adding more qubits actively corrects the errors already present in the system. The noise does not pile up. The noise cancels out. The machine becomes more reliable as it grows larger,
our sun,
and every physicist who has seriously studied this result understands, even if they speak carefully in public, that this behavior is not fully explained by our current picture of what computation is or where it happens. That is the central tension running through this entire story. So let us name it clearly. We have built machines that work. We know how to build them. We know how to operate them. We know how to program them. We know how to read their outputs. But what we cannot fully explain, what no one on Earth can explain with total confidence, is why they work in the deepest physical sense. Not just mathematically, not just operationally, but physically. Where does the computation live? What resource is being consumed? What part of reality is being asked to do the work? The machine works. That is not the mystery. The mystery is why. And that mystery leads all the way back to a paper published in 1985 by an Oxford physicist who made a claim so radical that most of his colleagues ignored it, dismissed it, or placed it in the category of interesting but impossible to prove. His claim was this: a quantum computer cannot operate inside a single universe. The computation, by physical necessity, must be distributed across parallel versions of reality, not as a metaphor, not as a convenient mathematical trick, but as a literal description of where the work is happening. That paper was written almost 40 years before Google Willow existed, and the data now coming out of quantum hardware laboratories looks disturbingly consistent with what he predicted. So the real question is not whether quantum computers are powerful. The real question is whether we have accidentally built a machine that proves the multiverse is real. And once you sit with the evidence, that question becomes much harder to laugh away than you might expect. Part 2. The refrigerator that should not exist. Before we talk about parallel universes and the structure of reality, we need to talk about a refrigerator. Not the refrigerator in your kitchen, something much stranger. Something so cold that if you walked into the room where it operates, your instruments would register it as one of the coldest places you had ever encountered. Colder, in fact, than almost anywhere in the observable universe. The devices used to run superconducting quantum processors like Sycamore and Willow operate at temperatures around 20 millikelvin. That is 20 thousandths of a degree above absolute zero. For context, absolute zero is the temperature where all thermal motion in matter theoretically stops. That temperature is minus 273.15 degrees Celsius. The dark side of the moon can drop to around minus 230 degrees Celsius. The cosmic microwave background, the faint leftover heat from the Big Bang that fills the universe in every direction, sits at about 2.7 Kelvin, or roughly minus 270 degrees Celsius. These quantum machines operate colder than the average temperature of outer space. The structure of one of these refrigerators does not look anything like what the word refrigerator normally suggests. It looks like a series of cylindrical stages hanging from the ceiling. Each stage is colder than the one above it. The temperature drops step by step, from around 50 Kelvin at the outer shield to 4 Kelvin at the next stage, then around 800 millikelvin, then 100 millikelvin, and finally down to the operational core of roughly 20 millikelvin. The entire assembly sits inside a cylindrical vacuum chamber lined with gold-plated copper shielding. It hangs like a chandelier designed by engineers who accidentally wandered into a fever dream. Microwave cables run down through the stages like neural pathways. They carry the pulses that communicate with the qubits at the bottom. In superconducting processors, those qubits are built around something called a Josephson junction. A Josephson junction is basically two superconducting materials separated by an extremely thin insulating layer, so thin that quantum tunneling can occur across it. Electrons, or more precisely Cooper pairs of electrons, can pass through the barrier without going over it. That has no classical equivalent. When these junctions are cooled close to absolute zero and operated under the right conditions, they behave like artificial atoms. They have discrete energy levels. They respond to microwave pulses in controlled ways. And most importantly, they can be placed into quantum superposition. This is where ordinary language begins to fail us, so we need to be careful. You have probably heard people say that a qubit can be 0 and 1 at the same time. That is technically true, but it is also slightly misleading in an important way. A qubit in superposition is not like a coin spinning in the air that is secretly either heads or tails and simply has not been revealed yet. It is genuinely in a combination of both states. That combination is described by something physicists call a probability amplitude. A probability amplitude is a complex number that contains both the likelihood of each outcome and something called phase. That phase determines how different superpositions interfere with one another, and this phase and interference are not small details. They are the entire game. Quantum computation is not mainly about storing more information in one bit. It is about using probability amplitudes to interfere. It amplifies computational paths that lead toward correct answers, and it cancels paths that lead toward wrong ones. The machine is not simply guessing faster, it is navigating a probability space through wave-like interference in a way that has no classical equivalent. A useful metaphor is noise-cancelling headphones. They work by producing a sound wave that mirrors the ambient noise, causing the two waves to cancel. Quantum algorithms do something similar with probability amplitudes. They are designed so wrong answers destructively interfere with one another, and right answers constructively reinforce one another. But this only works if the quantum states remain coherent. The delicate superpositions and phase relationships must survive long enough for the computation to finish. And this is where the engineering challenge becomes almost absurd. Quantum states are incredibly sensitive to disturbance. A single stray photon from room temperature thermal radiation, a vibration passing through the floor from a truck outside, electromagnetic interference from a nearby phone or power line. Any of these can cause decoherence. Decoherence is when the quantum state collapses into a classical state. And once that happens, the computation is destroyed. That is why the refrigerators exist. That is why the gold-plated shielding exists. That is why quantum computing laboratories are among the most carefully isolated environments ever built by humans. You are trying to maintain quantum states inside a physical system made of real matter, while the universe itself is constantly trying to destroy those states. Observation, in the quantum mechanical sense, does not only mean a human looking at something, it means any interaction with the environment. And that interaction is fatal to the computation. You are building something that can only exist in near-perfect isolation from the rest of reality. And yet, despite all of this, the machines work. The states survive long enough. The computation's complete. And with Willow, those systems become more stable as they grow larger. That is the opposite of what every engineering instinct says should happen. When you add more physical qubits, you add more matter. More possible coupling to the environment, more surface area for noise to enter. The laws of thermodynamics suggest this should make things worse. The data says it makes things better. There is one version of this story where that is just brilliant engineering, where the error correction codes are simply very good, where below-threshold behavior is an expected theoretical result finally showing up in hardware, and that version may be correct. But it sits beside another version, the version David Deutsch has been arguing for since 1985. That version says the stability is not only because of what the system is doing inside one universe, it is because of what it is doing across many universes at once. In that interpretation, the machine works because the computational load is distributed across parallel branches of reality. The error correction is, in some sense, a kind of quantum averaging across those branches. That is an enormous claim. But before dismissing it, you need to understand the mathematics that forced a physicist in 1985 to take it seriously. Because if you follow the arithmetic of quantum computing carefully, it leads you somewhere the observable universe simply cannot contain. Part 3. The arithmetic that breaks the universe. Let us do a little mathematics. Nothing complicated. Just multiplication and honest accounting. Because the most unsettling thing about quantum computing is not the hardware. It is the numbers, and when you follow those numbers to their conclusion, you are left with two possible explanations. Neither one is comfortable. Start here. A classical computer stores information in bits. Each bit is either 0 or 1. 2 bits can represent 4 possible states. 0, 1, 2, 3. 3 bits can represent 8 states. Every time you add another bit, the number of possible states doubles. With 10 bits, you have 1024 possible states. With 50 bits, you have more than 1 quadrillion possible states. But a classical machine only exists in one of those states at a given moment. It can move between states. It can process them sequentially, but it inhabits one state at a time. A quantum computer does something fundamentally different. A single qubit in superposition does not represent only 0 or 1. It represents a combination of both, described by probability amplitudes. 2 qubits in superposition represent all 4 2-bit states at once. 3 qubits represent all 8 3-bit states at once. 10 qubits represent all 1024 states simultaneously. 50 qubits represent more than 1 quadrillion states simultaneously. The system does not move through these states one after another. It inhabits all of them at once. It operates on all of them in parallel, and it produces its final output through interference. Now extend this to 300 qubits. 2 to the power of 300 is approximately 2 times 10 to the power of 90. That is a 2 followed by 90 zeros. That is the number of states a 300-qubit quantum computer exists in simultaneously. And here is where the accounting problem begins. The total number of atoms in the observable universe is estimated to be around 10 to the power of 80. A 300-qubit quantum processor operating in full superposition would manipulate a number of states that exceeds the total number of atoms in the observable universe. Everything we can see, in every direction, from every point in space, out to the edge of the observable cosmos. A 300-qubit system. Only 300. Google Willow has 105 physical qubits. IBM's roadmap targets thousands of qubits within this decade. People are already seriously discussing million-qubit systems within 20 years. The state space of those future machines would make 300 qubits look like a rounding error. Now, this is where someone usually raises an objection, and it is a fair objection. You might say, the system is not literally storing all those states in the same way classical memory stores data. The probability amplitudes are not physical objects sitting in physical locations. The computation is a mathematical description of quantum evolution. When you measure it, you only get one answer. So where is the paradox? The paradox is this. The computation demonstrably happens. The interference between those states demonstrably occurs. The correct answer emerges from a process that, if classical, would require examining an astronomical number of possibilities in parallel. The machine produces results that can only be explained by something that was, at some stage in the process, evaluating an exponentially large space of possibilities at the same time. You cannot get those results from a process that was only ever in one state at a time. The mathematics of the output requires that the intermediate steps involve something operating across the entire superposition simultaneously. So the real question is not whether the system was in all those states. Quantum mechanics says it was. The question is, what physical substrate was hosting that information? Where was it? In a 300-qubit system, the state space exceeds the information capacity of every atom in the observable universe. You cannot store 2 times 10 to the 90 amplitudes in 10 to the 80 atoms. The arithmetic does not work. You run out of universe before you run out of states. Physicists have a name for the mathematical space where quantum states live. It is called Hilbert space, and Hilbert space, in a very precise sense, is larger than physical space. That is not a metaphor. It is a mathematical fact. The space needed to fully describe even a moderately sized quantum system exceeds the dimensionality of any physical space we have ever observed or measured. The computation is happening in a space larger than the universe. So where is it? This is not just a dramatic question. It is a genuine open question in the foundations of physics. And the person who pushed hardest on this question was David Deutsch. He refused to treat it as merely philosophical. He insisted it had a physical answer. He asked this question in 1985, before quantum computers existed as real hardware. Back then, they were theoretical objects, but he asked it using the serious tools of theoretical physics. And the answer he reached is one the scientific community has been wrestling with ever since. If the information cannot be stored in this universe, then there is only one alternative. It is being stored somewhere else. Part 4. The physicist everyone ignored. In 1985, a young physicist at the University of Oxford named David Deutsch published a paper in the Proceedings of the Royal Society of London. The title was Quantum Theory, the Church-Turing Principle, and the Universal Quantum Computer. It is one of the most important papers in the history of computer science, and for a long time it was also one of the most ignored, not because it was wrong, but because it was too right in a direction most physicists were not prepared to follow. Deutsch's central claim was deceptively simple. He argued that a quantum computer, by the nature of what it does, cannot be performing its computation inside a single universe. The exponential resource requirement, the one we just walked through, makes that physically impossible. The information being processed, the simultaneous evaluation of exponentially many possibilities, requires a physical substrate. That substrate cannot be the matter in our observable universe. Therefore, the substrate must be somewhere else. And the only coherent physical picture where somewhere else makes sense, Deutsch argued, is the many worlds interpretation of quantum mechanics. To understand why Deutsch went there, we need to go almost 30 years further back, to a Princeton graduate student named Hugh Everett III. Everett was working on his doctoral thesis in 1957 under John Wheeler. He was trying to solve a problem that had haunted quantum mechanics since its beginning. That problem is called the measurement problem. In standard quantum mechanics, as shaped by people like Niels Bohr and Werner Heisenberg in the 1920s, quantum systems evolve in superposition according to Schrödinger's equation, smoothly, deterministically, following precise mathematical rules, until they are measured. At the moment of measurement, the superposition collapses. One outcome is selected. The probability amplitudes for all other outcomes vanish. This is called wave function collapse. But the problem is that wave function collapse is not described by Schrödinger's equation. It is an extra postulate added onto the theory, not because it follows from the mathematics, but because it matches what we observe. Every time we measure a quantum system, we see one outcome. So collapse must happen. But the equation itself says no such thing. The equation says the superposition continues evolving, branching, never collapsing. Something is wrong, or something is incomplete, and every physicist who has seriously worked on the foundations of quantum mechanics knows this. Everett's solution was radical because of how simple it was. He asked, what if the equation is right? What if there is no collapse? What if every possible outcome actually happens when a quantum measurement occurs? Not one winning while the others disappear, not one selected while the rest vanish, but all outcomes happening simultaneously in parallel branches of one universal wave function. The measuring device branches, the experimenter branches, the laboratory branches, the planet branches, the galaxy branches. Each version is real. Each version is unaware of the others because the branches no longer interact. This became known as the many worlds interpretation, also called the Everett interpretation. And in 1957 it was received about as coldly as you would expect. Niels Bohr, the towering figure of quantum mechanics, had spent decades defending what became known as the Copenhagen interpretation. That view said, quantum mechanics is a tool for predicting measurement outcomes, not necessarily a description of what reality actually is. Questions about what exists between measurements were often treated as meaningless. Bohr's influence over mid-20th century physics was enormous, and his dismissal of anyone asking, but what is actually happening, was almost final. Everett's thesis was reduced, shortened, and published in a less ambitious form. It attracted almost no attention. Everett eventually left academic physics completely. He went to work for the Pentagon. He worked on nuclear strategy and operations research during the Cold War. By most accounts, he became a deeply unhappy man. He drank heavily and died of a heart attack in 1982 at only 51 years old. He never saw his idea rehabilitated. He never knew that decades later it would become one of the most seriously discussed frameworks in the foundations of physics. Not merely as a strange possibility, but arguably as the most conservative interpretation of quantum mechanics, because it simply takes the mathematics at face value without adding a separate collapse rule. David Deutsch knew Everett's work, and Deutsch took Everett seriously, not as a philosophical option, but as the literal physical picture of what quantum mechanics was describing. So when Deutsch analyzed what a quantum computer would actually be doing, the many worlds picture was not just compatible, it looked necessary. In Deutsch's view, a quantum computation is interference between parallel computations happening simultaneously in parallel branches of the wave function. The reason the machine can evaluate an exponentially large problem space is that the exponentially many evaluations are distributed across exponentially many parallel realities. Each branch does a small part of the work. The interference between branches produces the answer. You collect the answer in your branch, but the labor was done everywhere. This is not a small claim. Deutsch was not just saying many worlds is an interesting interpretation. He was saying the operational behavior of quantum computers only makes sense if you take many worlds seriously as a physical description. He was saying the hardware, when it runs, is evidence that branching is real. Other universes are not just possible. They are not just mathematical. They are load-bearing. They are doing actual computational work. And this is what makes the story so strange. When Deutsch published that in 1985, quantum computers did not yet exist. They were theoretical. Sycamore and Willow were decades away. He was making a prediction about what these machines would imply about reality before anyone had built one. Now we have built them. Now they are running, and they are doing exactly what his framework suggested they would do. They are performing computations that exceed the physical resources of any single universe. The man many of his colleagues ignored in 1985 may have been quietly, patiently right, but we are still in the territory of interpretation. You could still argue that there are alternative frameworks that do not require committing to parallel universes. So now we need to talk about the experimental evidence, because in 2022, the Nobel Committee awarded physics' highest honor to 3 people whose work, taken together, closed many of the comfortable philosophical exits from Deutsch's conclusion. Part 5. The Nobel Prize that quietly confirmed it. In October 2022, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to 3 experimental physicists: Alain Aspect from the University of Paris-Saclay, John Clauser from J.F. Clauser and Associates, and Anton Zeilinger from the University of Vienna. The official announcement said they received the prize for experiments with entangled photons, for proving violations of Bell inequalities, and for pioneering quantum information science. That description is completely accurate, but if you understand what Bell inequalities are and what it means to violate them, then that announcement becomes one of the most important sentences ever written in a Nobel Prize statement. To understand why, we need to go back to 1964. That year, an Irish physicist named John Stuart Bell published a paper that changed the foundations of physics. Bell was working at CERN, and he was trying to settle an argument that had been burning in physics since 1935. That earlier argument began when Albert Einstein, Boris Podolsky, and Nathan Rosen published what became known as the EPR paper. Einstein's problem was with something he called spooky action at a distance. Quantum mechanics seemed to suggest that measuring one particle could instantly affect the state of another entangled particle far away. No matter how much distance separated them, Einstein could not accept that. He believed quantum mechanics, as it existed at that time, was incomplete. He thought there had to be hidden variables, some deeper layer of physical reality, some local information carried by the particles themselves, something that already determined their measurement outcomes before we looked. In Einstein's view, the apparent weirdness was only ignorance. The particles already knew what they were going to do. We simply did not have access to that information. But Bell showed something remarkable. He showed that Einstein's intuition, as reasonable as it sounded, made a testable prediction. If particles carried hidden variables that locally determined their measurement results, then the correlations between distant entangled particles had to obey certain mathematical limits. Those limits are called Bell inequalities. And here is the critical point. Quantum mechanics predicted those limits would be violated. So now the two views made different numerical predictions. A hidden variable universe predicted one result. Quantum mechanics predicted another. Bell had transformed a philosophical argument into a laboratory experiment. The first serious experimental test came in 1972. John Clauser and his collaborator Stuart Friedman tested entangled particles. Their results favored quantum mechanics over hidden variables. But the experiment still had loopholes. There were technical problems involving detector efficiency and measurement timing. A determined supporter of hidden variables could still find a way to escape. Almost another decade passed before Alain Aspect, working in Paris in the early 1980s, performed a series of experiments designed to close the biggest loopholes. Aspect's results, published in 1981 and 1982, violated Bell inequalities with very strong statistical confidence. Local hidden variables were in serious trouble. But even then, the debate did not fully end. It took until 2015 for loophole-free experiments to close the case more decisively. One of the most important was conducted by Ronald Hansen's group at Delft University. These experiments closed both the detection loophole and the locality loophole at the same time. They used entangled electrons separated by more than a kilometer. The measurements were made so quickly that no signal traveling at the speed of light could have passed between the detectors before both measurements were completed, and the result was clear. Bell inequalities were violated again, decisively. Without the escape routes earlier experiments had left open, the conclusion of this 30-year experimental program, the conclusion that helped earn Aspect, Clauser, and Zeilinger the Nobel Prize, was this: local hidden variable theories are ruled out. The particles do not carry pre-written answers. There is no deeper classical reality underneath quantum mechanics where everything is secretly decided in advance. The universe, at its most fundamental level, does not work the way Einstein hoped it did. The correlations between entangled particles are real. They are non-classical, and they cannot be explained by any mechanism where information simply travels locally between measurement sites. But we need to be careful here. This is where popular science often goes too far. Violating Bell inequalities does not mean measuring one entangled particle sends a usable signal to the other. It does not mean information travels faster than light. Quantum mechanics has something called the no-signaling theorem. It says you cannot use entanglement to send classical information instantly. Aspects, experiments, and all the Bell tests after them are consistent with that. You cannot use entanglement to send a message faster than light. But the correlations are real. They exist. They are stronger than anything a classical local model can produce. Something is connecting those particles in a way that is not mediated by any ordinary classical signal. Something about the structure of reality produces outcomes at two separated detectors that are correlated beyond any local explanation. The universe does not compute locally. That phrase matters. It means the relationship between two distant entangled particles is not maintained by some mechanism living in the space between them. It is a relationship that is, in some deep sense, non-local. And now this loops directly back to the question we started with. If quantum mechanics is non-local, if correlations between entangled particles cannot be explained by local hidden variables, if the universe does not keep all its information in local packets, then the question of where quantum computation happens becomes even more urgent. These machines are non-local. The resources they use are non-local. The correlations they exploit cannot be explained by any mechanism that fits comfortably inside our ordinary picture of space and time. In Deutsch's framework, this is exactly what you would expect. The computation is distributed across parallel branches of reality. Interference between those branches produces correlations that look non-local from inside any single branch. The Nobel Prize did not directly prove Deutsch was right, but it did close off the most comfortable alternative. The idea that hidden variables carry the information locally. The idea that beneath quantum weirdness there is a classical story waiting to be found. That story is experimentally ruled out, and the stories left behind are much stranger. What remains is entanglement as a real physical resource, something real, something maintainable over enormous distances, something that, when scaled up, becomes the engine that makes quantum computers run. But where does that resource live? How far can it stretch? In 2017, a satellite answered that question in a way that should have made far bigger headlines. Part 6. The verification collapse. There is a problem quantum computing creates that almost nobody discusses loudly enough, and it strikes directly at something human civilization has relied on since the beginning of organized science. The problem is verification. The problem is this: we are building machines whose outputs we may not be able to check. That is not a small engineering inconvenience. It is a structural feature of quantum computation itself. When a classical computer runs a calculation, you can verify the result. You can run the calculation again. You can use another algorithm to cross-check it. In many cases, you can work backward from the output. The process is auditable. There is a chain of reasoning from input to output. At least in principle, each step can be inspected. The history of mathematics and science depends on this ability. Peer review works because results can be reproduced. Proofs can be checked. Claims can be tested. But quantum computing begins to break that relationship. In 2020, a group of researchers, including Thomas Viddick at Caltech, published a result in complexity theory that did not receive nearly enough public attention. The result is written as
Emipari.
At first, that looks like alphabet soup, but once you unpack it, it becomes deeply unsettling. MyPSay is the class of computational problems that can be verified by a classical computer interacting with two quantum provers. Those provers are quantum systems that share entanglement. RE is the class of recursively enumerable problems. In rough terms, that means problems that are solvable at all, including problems that may take arbitrarily long. The theorem says quantum entanglement gives verifiers access to a class of problems vastly larger than anything classically verifiable, enormously larger, almost incomprehensibly larger. The implication for quantum computing is this. As quantum computers become more powerful, their outputs will increasingly move beyond the verification capacity of classical systems. A sufficiently large quantum computation will produce results that no classical computer can fully confirm or deny, no matter how big it is, no matter how long it runs. From the point of view of classical physics, the quantum computer becomes an oracle, a black box. You put the question in, an answer comes out, and there may be no independent classical way to know whether that answer is correct. Think about what that means for science. The scientific method depends on reproducibility. An experiment must be repeatable. A result must be verifiable. A claim must be checkable. These are not small procedural preferences. They are the load-bearing assumptions of empirical knowledge. Remove them, and you are no longer doing science in the ordinary sense. You are doing something closer to trust in a process. Now, we are not fully there yet. Current quantum computers are still small enough that their outputs can be spot-checked by classical methods, even if that checking is expensive, but the direction is clear. Willow's performance is already pushing into areas where full classical verification becomes impractical. IBM's roadmap, Google's roadmap, Microsoft's roadmap, all of them are moving towards systems where verification may become impossible long before the machines reach their most ambitious applications. This creates a strange situation. We may have machines that can solve problems of enormous practical importance: drug discovery, material science, financial optimization, logistics, cryptography, but we may have to trust their outputs without being able to fully verify them independently. The trust will be placed in the process, in the physics, in the theoretical framework that says the machine should work. But the theoretical framework is quantum mechanics, and the physical meaning of quantum mechanics is exactly what physicists still disagree about. So we are being asked to trust the output of a machine whose operating principle is still philosophically disputed, using a method our civilization may not be able to check. That is the verification collapse. And it is coming faster than most people realize. This might sound abstract, but it has very real consequences. When quantum computers are used to discover new drugs, they may model molecular interactions in ways classical computers cannot. But the difference between a correct answer and a believable wrong answer may not become obvious until clinical trials, or worse, after the drug has already affected people. When quantum systems are used in financial modeling, a verification gap could allow model errors to move into real economic systems before anyone catches them. And when quantum computers are eventually aimed at encryption, the situation becomes different again, because then the output is not just hard to verify, it is designed to break things we rely on. But here is the other side. The machines are becoming more stable, the error rates are falling. Willow's below-threshold behavior means that, at system scale, quantum computers are moving toward reliable and reproducible outputs. And that raises a deeper question. Why are they converging? Why does adding more qubits not cause the noise to accumulate like it should? What is doing the stabilizing? The engineering answer is quantum error correction codes, and that answer is true as far as it goes. But it does not fully answer why those codes work, why below-threshold behavior is achievable at all, why the system behaves as if it has access to error correction resources beyond what any single physical system should possess. To answer that, we may need to look not only at the hardware, we may need to look at the space across which quantum correlations can operate, and that space is larger than the laboratory, much larger. Part 7. The Error Correction Paradox. Quantum error correction sounds like an engineering problem, but the more deeply you understand it, the more it begins to look like a philosophical one. To understand why, we need to go back to 1995. That year, a mathematician and physicist named Peter Shor published a paper showing that quantum error correction was theoretically possible. Yes, the same Shaw whose algorithm later threatened modern encryption. At that time, this was not obvious at all. Before Shaw's paper, many physicists believed decoherence would make large-scale quantum computing permanently impossible. The argument was simple. Quantum states are fragile. Errors accumulate. And quantum mechanics does not allow you to simply copy a qubit the way you copy classical data. So there seemed to be no way to catch and correct errors before they destroyed the computation. Shaw's insight was brilliant. He showed that you could protect a logical qubit by encoding it redundantly across multiple physical qubits. But you could do this in a way that allowed errors to be detected and corrected without directly measuring the underlying quantum state. You could measure certain relationships between qubits. These are called stabilizer measurements. They tell you whether an error occurred without revealing what the actual protected qubit state is. That preserves the quantum information while allowing the error to be corrected. It is a beautiful idea. The theory worked, but the big question was whether hardware would ever be good enough to make it practical. The answer depended on the threshold theorem. The threshold theorem says that if the error rate of physical qubit operations falls below a certain critical value, then quantum error correction can reduce the logical error rate. For many architectures, that threshold is roughly around 1%, though the exact number varies. Below that threshold, you can make the computation as reliable as you want by using more physical qubits per logical qubit. Below the threshold, more physical qubits means lower logical error rates. Above the threshold, more physical qubits means more total errors. The threshold is the critical point. Google Willow, in December 2024, showed the first real hardware evidence of below-threshold scaling across multiple code distances. Code distance measures how many physical qubits are used to encode one logical qubit. Willow showed that as code distance increased, the error rate decreased, and it decreased in the exponential way the threshold theorem predicted for below-threshold hardware. This was experimental confirmation of a theoretical result that had been waiting in the air since 1995. It can actually be done, but here is the paradox stated as clearly as possible. To correct errors, you need measurements, but to measure a quantum system is to interact with it. And interaction usually causes decoherence. Decoherence causes errors, so you are using a process that can create errors in order to correct errors. At first glance, that sounds circular, almost self-defeating. So why does it work? The formal answer is that stabilizer measurements are carefully designed. They extract only enough information to identify the error syndrome. That means the pattern of errors that occurred. But they do not extract information about the logical quantum state being protected. They measure relationships between qubits, not the qubits themselves. Because they access only the error information and not the logical information, they do not collapse the logical superposition. The error is identified. The error is corrected. The computation continues. This is mathematically rigorous. It works. But it depends on something subtle. The errors must be local and independent. Each physical qubit must fail mostly on its own. The failure of one qubit must not cause structured, correlated failures in many others. If the errors are correlated, the codes can fail, because quantum error correction codes are designed for independent random errors. Correlated errors can look like logical errors to the syndrome measurements, and those cannot be corrected without destroying the computation. So, the reason quantum error correction works depends on the system behaving as if each physical qubit is interacting mainly with its local environment. The noise is treated as local. The corrections are local. The codes work locally, but the quantum states being protected are not local. They are entangled. They are non-local. And in Deutsch's framework, they are distributed across parallel branches of reality. So the computation being protected is fundamentally non-local. Yet the protection is being performed by local operations. That combination is strange. Local error correction is protecting non-local computation, and it works only because these two dynamics operate on different timescales and through different mechanisms. Noise couples to qubits through local physical interactions. Entanglement operates at a deeper level than ordinary local interactions. Quantum error correction catches the errors before they disrupt the deeper structure where the computation lives. If that deeper structure is the universal wave function, if the computation is genuinely distributed across parallel branches, then what Willow demonstrated is that those branches can be kept coherent and aligned using local operations performed inside a single branch. In that interpretation, you are doing error correction in one universe, but the stability is propagating into a computation happening across many. Below-threshold behavior is evidence not only that the engineering works, it may also suggest that the structure being protected is more robust than any classical system because it is not limited to one physical copy of itself. That is speculative, but it is consistent with what we know, and quantum machines are not the only things showing this non-classical robustness. In 2017, a satellite showed us that entanglement does not care about the distance between the stars. Part 8. The satellite that proved it is real. In 2017, a Chinese research satellite named Mikius was orbiting Earth. It was named after the ancient Chinese philosopher Mozi, who performed some of the earliest recorded experiments in optics. The satellite was in a sun-synchronous orbit roughly 500 kilometers above Earth. It had been launched the previous year by a team at the Chinese Academy of Sciences led by physicist Jianwei Pan. Its purpose sounded simple when described, but its implications were staggering. It was designed to distribute quantum entanglement between ground stations separated by distances that had once seemed impossible. In 2017, Mikius established entanglement between photons detected at 2 ground stations. One station was in Dellinger, the other was in Lijiang. They were separated by more than 1,200 kilometers. That is roughly the width of France and Germany combined, or around the distance from London to Athens. The satellite generated pairs of entangled photons. It sent one photon from each pair to one ground station and the other photon to the second station, and the entanglement survived. The measurement correlations between the two stations violated Bell inequalities by more than 11 standard deviations. There was no ambiguity. The entanglement was real. The connection held. The following year, Mikius was used for a quantum key distribution test between Beijing and Vienna. Those cities were separated by more than 7,000 kilometers. Using a chain of ground stations and the satellite as an intermediary, researchers demonstrated the first intercontinental quantum-secured communication. This proved that quantum cryptography could work at global scales. Communication whose security is guaranteed not by mathematical difficulty alone, but by the laws of physics. So why does this matter for the question we have been building toward? Because the Mikius experiment established something laboratory demonstrations had suggested, but never shown so dramatically. Entanglement does not care about distance. Once a quantum correlation is established between 2 photons, it can survive regardless of the separation between them. 1,200 kilometers of atmosphere, weather, Earth's curvature, relativistic effects from orbital velocity. None of it destroyed the entanglement. The relationship between those photons persisted across a scale far larger than any laboratory. And here is the critical implication for quantum computing. If entanglement is a resource, and it is the core resource quantum computation exploits, then that resource is not confined to the physical volume of the hardware that generates it. The correlations that make quantum computation possible operate on scales with no classical equivalent. There is no classical mechanism by which one particle's property can remain perfectly correlated with another particle 1 to 200 kilometers away without a direct physical connection. No wire, no field in the ordinary sense, no signal traveling between them in the available time. And yet the correlations are there. The no signaling theorem tells us we cannot use this to send information faster than light. The correlations are real, but we cannot choose them in a way that transmits a message. So this is not a loophole in special relativity, but it is something stranger. It means the relationship between the particles is maintained by something that is not a physical signal moving through the space between them. The universe maintains correlation without sending a message. The relationship exists without transmission. What kind of physical picture can explain that? In the Copenhagen interpretation, you simply do not ask. The wave function is treated as a tool for predicting measurement results. There is no real connection to describe. There is only mathematical correlation. Questions about the physical mechanism behind it are often treated as meaningless. But we have already seen that this dismissal was never settled physics. It was partly a methodological preference defended strongly by Bohr's influence. Bell experiments and the 2022 Nobel Prize confirm that something non-classical is happening. The Mikius experiments confirm that it holds across planetary scales. In the Everett framework, the explanation is that the 2 particles are part of one global quantum state. One wave function contains both of them, regardless of how far apart they are in space. When you measure one particle in one branch, the corresponding particle in the pair is found in the correlated state in that same branch. The correlation is maintained because the two particles never stopped being part of the same quantum state, even when distance separated them. In this picture, space is not the deepest arena where quantum events happen. Quantum states are deeper. Quantum states do not have a location the way classical objects do. This is not only interpretation, it has architectural consequences for how quantum computers may be built. In principle, components of a quantum computer could be separated into different buildings, one day perhaps even different continents, and still exploit entanglement for computation. The Metius experiments showed that entanglement can survive through real physical environments at scales relevant for real infrastructure. And the fact that it survives without a classical signal means the resource quantum computers use is not bound by ordinary spatial constraints. Which brings us to a theory published in 2013, a theory proposing something even more radical, that space itself may be created by entanglement, that the geometry of the universe may be, at its deepest level, a consequence of quantum connections, and that quantum computers may be manipulating the fabric of spacetime itself. Part 9. The wormhole interpretation. In 2013, two theoretical physicists published a paper with a title that looked almost like an equation. EPR. The ER stands for Einstein-Rosen. That refers to the theoretical structure more commonly known as a wormhole, a connection between two distant regions of spacetime predicted by general relativity in a 1935 paper by Albert Einstein and Nathan Rosen. The EPR stands for Einstein, Podolsky, and Rosen. That refers to the same 1935 paper about quantum entanglement and its strange non-local behavior that we discussed earlier. The authors of the 2013 paper were Juan Maldacena, one of the most cited physicists in the world, and Leonard Susskind, another giant of theoretical physics. Their claim was extraordinary. They argued that wormholes and entanglement are not merely similar ideas. They may actually be the same thing. The ER-EPR conjecture proposes that any two entangled particles are connected by a microscopic wormhole, not as a metaphor, not as a poetic image, not as a mathematical coincidence, but as a possible physical description of the structure of spacetime itself. In this view, entanglement is not simply a correlation between two particles that somehow survives over distance. Entanglement is a geometric connection, a tiny, non-traversable bridge in spacetime linking the two particles. The particles are not only correlated, they are connected by a thread of spacetime itself. Now, it is important to be clear, these wormholes are not traversable. You cannot travel through them. You cannot send a message through them. You cannot use them like science fiction portals. They are not the kind of wormholes a spaceship flies into. They are topological connections, structures inside space-time geometry that link two regions without allowing matter or information to pass through. That is why entanglement still cannot be used for faster-than-light communication. Even in this framework, the bridge exists, but it cannot carry a usable signal. The no-signaling theorem remains safe, but the implication goes much deeper than communication. If EPR is correct, then spacetime geometry is not the background stage where quantum physics happens. Instead, spacetime geometry may be produced by quantum physics. More specifically, the structure of spacetime, the network of connections we experience as distances and directions, may be a consequence of the entanglement structure of quantum states. More entanglement means more connectivity. Less entanglement means the geometry begins to pull apart. In the limit of zero entanglement, the geometric connection disappears. Space itself dissolves. This is the idea of emergent spacetime. The proposal that the three dimensions of space and one dimension of time we experience are not fundamental. They are derived. They emerge from a deeper layer of quantum information, a layer where the most important variable is not position. It is entanglement. In this picture, asking where is the quantum computation happening is not just a question about location. It becomes a question about what creates location in the first place. So what does this mean for quantum computers? A quantum computer is a network of entangled qubits. As the number of qubits grows and the entanglement structure becomes more complex, the system in the EPR framework may be generating an increasingly complex geometric structure. The processor is not simply manipulating quantum states. In a technical sense, it may be constructing and navigating quantum geometry. The computation happening inside a large quantum processor might be, at a level we do not yet fully understand, a form of geometric manipulation, a rearrangement of space-time connections encoded inside the entanglement pattern of the qubits. This sounds like science fiction, and the honest answer is that right now it remains theoretical and unconfirmed experimentally. The Homs-EPR conjecture has not been proven from first principles. It has not yet been tested by a direct experiment that could falsify it. It is a proposal, a powerful, mathematically sophisticated, highly influential proposal from some of the most respected people in theoretical physics. But it is still a conjecture. Maldacena and Susskind themselves have been careful. They have noted that the conjecture works most cleanly in certain mathematical limits and may not transfer directly into the real universe in the simplest possible form. But physicists take it seriously because it connects things that desperately need connecting. It connects quantum mechanics to general relativity, two theories that have resisted unification for a century, and it connects them through one concept: entanglement. It gives a geometric picture of why entanglement looks non-local, because space-time geometry itself may be produced by entanglement structure. In that picture, non-local correlations are not puzzling. They are the entanglement structure expressing itself. And it points toward a possible answer to one of the deepest questions in physics. What is gravity, and how does it fit with quantum mechanics? If EPR is correct, then quantum computers are not just calculating tools. They are engines that construct and move through geometric structures in a deeper space beneath the space-time we observe. The calculation Sycamore performed in 200 seconds was not just a quantum calculation. It may have been a navigation through a geometry existing below ordinary space and time. And the reason classical computers could not simulate it was not only that it required too many states. It may be that the geometric structure it traveled through has no classical description at all. But even this may not be the deepest layer, because before space-time, before particles, before quantum fields, there may be something even more fundamental. Something a physicist who spent his career standing between quantum mechanics and general relativity spent his final decades trying to name. Part 10. The information layer beneath reality. John Archibald Wheeler was one of the most influential American physicists of the 20th century. He coined the term black hole. He worked with Niels Bohr on nuclear fission. He was Richard Feynman's doctoral advisor. He was one of those rare scientists who combined deep technical skill with a real hunger for the biggest possible questions. And late in his career, in his 70s and 80s, Wheeler became increasingly focused on one question. Eventually, he compressed that question into 3 words: it from bit. The idea behind it from bit is this: every physical thing, every particle, every field, every region of space-time, every observable property of every system in the universe may derive its existence from information, not information in the casual everyday sense, but information in the strict technical sense. Binary distinctions, yes or no answers, the fundamental logical structure behind measurement and observation. In Wheeler's view, the universe is not made primarily of matter and energy that happen to carry information. The universe is made of information. Matter and energy are what information looks like when it takes physical form. The it of the physical world comes from the bit of binary observation. This is a deep and intentionally strange claim. It means the question, what is the universe made of, may not ultimately be answered by atoms, or quantum fields, or strings, but by distinguishable states, by differences, by the fact that some things are not other things, by the fact that some properties take one value instead of another, by the fact that measurement gives a definite outcome instead of endless ambiguity. In this picture, the physical world is the system that generates and processes those distinctions. This claim is not only philosophical, there is a physical result pointing in the same direction. It is called Landauer's principle. In 1961, Rolf Landauer, working at IBM, proposed that erasing information has a physical cost. Specifically, resetting a bit from an unknown state to a known state must release a minimum amount of energy. That energy is equal to the temperature multiplied by Boltzmann's constant multiplied by the natural logarithm of 2. At first, this sounds like a tiny technical detail, but it is not. It means information erasure produces heat. It means information processing is a physical process with thermodynamic consequences. Information is not just a description of reality. Information is part of reality. For about 50 years, Landauer's principle was difficult to test directly. Then in 2012, an experiment at the University of Lyon confirmed it. A team led by Sergio Ciliberto used tiny colloidal particles in a controlled potential well. They showed that erasing one bit of information dissipates exactly the minimum amount of energy Landauer's principle predicted within experimental error. Since then, the result has been confirmed multiple times. Information erasure has a thermodynamic cost. Information has physics. Information is physical. This connects to another idea from general relativity and black hole thermodynamics. The holographic principle. In the 1990s, work by Jacob Bekenstein, Stephen Hawking, Gerard 't Hooft, and Leonard Susskind helped establish something shocking. The maximum information content of any region of space is proportional not to the volume of that region but to its surface area. The boundary of a region can encode only a certain amount of information, and that information limit constrains everything that can happen inside the region. Information is not stored primarily in the three-dimensional bulk. It lives on the two-dimensional boundary. The holographic principle has its clearest mathematical expression in the ADS-CFT correspondence developed by Juan Maldacena in 1997. ADS-CFT gives a concrete duality between a theory of quantum gravity in a higher dimensional curved spacetime and a quantum field theory on the boundary of that spacetime. It is one of the most precise and powerful ideas in theoretical physics. It works mathematically, and it suggests that the three-dimensional world we experience may, in a technical sense, be a projection of information encoded on a lower dimensional surface. So what does this mean for quantum computers? If matter is information, if spacetime is information, if the deepest structure of reality is the processing and encoding of distinctions, then a quantum computer is not just a machine processing information about reality. A quantum computer is a piece of reality doing what reality does at its deepest level. It is information processing information. It is the universe computing itself. The reason quantum computers can access exponentially large state spaces may not only be clever engineering, it may not only be non-classical physics. In the information-first picture, the reason is that the fundamental substrate of reality has an exponential capacity that no classical system inside a single branch of spacetime can match. Quantum computers tap into that capacity because, at their operating level, they are closer to the information layer than classical computers are. They are not running above the substrate. They are running inside it. This gives Wheeler's phrase, "it from bit," a new operational meaning in the age of quantum computing. The bit from which the it comes is not just a metaphor. It may be the computational substrate itself. And quantum computers, in this view, are windows into that substrate. Machines that reveal, through their outputs and capabilities, the information-theoretic structure of reality beneath everything else. The universe may be, at its deepest level, a computation. And if it is, we have just built a machine that speaks its language. Part 11. Encryption is already on a timer. Now let us come back to Earth for a moment. Because all of this, parallel universes, entanglement over 1-200 kilometers, the information layer beneath reality, may sound like it belongs only in physics journals and late-night philosophy. But one of its consequences is already sitting inside government planning documents. It is connected to a competition that began in 2016 and finished in 2024, and it has real consequences for the security of every financial transaction, every private message, and every classified communication on Earth. In 2016, the National Institute of Standards and Technology, known as NIST, launched a public competition. NIST is the American federal agency responsible for setting technical standards. They were looking for new cryptographic algorithms to replace the ones that currently protect much of digital communication on Earth. Why? Because of a quantum algorithm published in 1994 by Peter Shor, the same Peter Shor who proved quantum error correction was possible. Shor's algorithm showed that a sufficiently powerful quantum computer could factor large integers exponentially faster than any known classical algorithm. This matters because RSA encryption, the foundation of much public key cryptography, relies on the difficulty of factoring large numbers. For a classical computer, factoring a number made from 2,000-digit primes would take longer than the age of the universe using the best-known approaches. But Shor's algorithm, running on a large fault-tolerant quantum computer, could do it in hours, maybe even faster. The mathematical foundation of internet security would become as easy to break as a padlock with the combination written on it. NIST's competition ran for 8 years. It attracted hundreds of submissions from cryptographers around the world. In 2024, the final post-quantum cryptographic standards were published. The primary algorithms included Crystal's Kyber for key encapsulation, Crystal's Dilithium and Falcon for digital signatures, and Sphinx S Plus as a hash-based backup option. These algorithms are based on mathematical problems believed to be difficult even for quantum computers. Many involve lattice structures rather than integer factoring. So far, no Shor-like quantum speedup is known against them. The transition to these standards is now underway across governments and financial systems, but it will take years to fully deploy. And here is the important part. This transition is happening before large, fault-tolerant quantum computers exist. That is not paranoia. It is because of a strategy called Harvest now, decrypt later. Intelligence agencies, foreign governments, and advanced criminal groups can record encrypted traffic today. Banking transactions, diplomatic communications, military exchanges, private messages. They may not be able to decrypt them today, but they can store them. And once large quantum computers become available, they may be able to decrypt what they collected years earlier. Communications happening right now, protected by encryption that would currently take longer than the age of the universe to break, could become readable the moment someone builds a Shor-capable quantum processor. That is why the national security world takes this seriously. The move to post-quantum cryptography in government systems is being treated as urgent, not theoretical, not eventual. Urgent. Multiple governments have made assessments about the timeline to quantum machines capable of running Shor's algorithm at useful scale. The fact that NIST completed its standards in 2024 and deployment is moving through 2025 and 2026 tells you something. It tells you the people watching this closely do not believe there is unlimited time left. So how much time is actually left? No one knows for sure. Willow's 105 qubits are still far from the millions of physical qubits likely needed to attack real-world RSA keys. Many reputable estimates suggest a Shor-capable machine is still a decade or more away, but timelines in this field have surprised people before. Usually, things have taken longer than expected. But Willow's error correction results also surprised many people with how quickly progress can shift, so it would be unwise to assume the timeline is fixed. The cryptography story matters because it shows how quantum computing changes the world quietly before the public notices. The encryption standards you rely on every day for banking, medical records, private communication are being replaced right now, not because quantum computers have already broken them, but because the experts believe the threat is real enough to spend billions preparing for it. That is not hype. That is the signal, and encryption is only the beginning. Because quantum computing is not developing alone. It is developing alongside another technology that has already become one of the most transformative forces of the early 21st century, artificial intelligence. And the combination of quantum computing and AI creates possibilities and risks that neither technology could create by itself. Part 12. The AI and quantum convergence. There is a conversation happening right now between disciplines, in research labs, at conferences, in the hallways between quantum physicists and machine learning engineers. And it is the kind of conversation that often stays inside technical rooms instead of press releases. The question being asked is simple on the surface. What happens when quantum computing and artificial intelligence stop being separate fields? What happens when they begin to merge into one system? Not two parallel tools solving separate problems, but an integrated architecture where each technology amplifies the other in ways neither could achieve alone. The reason this question is being asked now is that both technologies are maturing at the same time, and the places where they touch are becoming practical, not just theoretical. The most immediate connection is already happening in laboratories. Current quantum computers are often called NISQ devices. That stands for Noisy Intermediate Scale Quantum. These machines produce outputs affected by hardware errors and environmental noise. To extract useful information from them, researchers need advanced classical post-processing. And machine learning algorithms are surprisingly good at that job. They can identify systematic patterns inside noisy quantum outputs. They can learn hardware-specific error signatures that vary from chip to chip. They can optimize the compilation of quantum circuits in ways human engineers might not anticipate. AI is already acting as a translator between quantum hardware and human-readable results. That is useful, but it is only the modest beginning. The more consequential direction is the reverse, using quantum computation to enhance artificial intelligence itself. To understand why that matters, you need to know where the computational cost of modern AI actually lives. The answer is linear algebra, more specifically matrix multiplication at enormous scale. Training a large language model or running inference on one requires multiplying matrices with billions or trillions of entries, again and again, across millions of training steps. The hardware behind modern AI, the GPU clusters consuming megawatts of electricity inside data centers, is basically optimized matrix multiplication machinery. It is incredibly good at this, but it is also approaching physical limits in speed and efficiency. Quantum algorithms may offer a different path. One important example is the HHL algorithm. It was developed in 2009 by Aram Harrow, Avinatan Hasidim, and Seth Lloyd. HHL provides a quantum method for solving certain linear systems with a polynomial speedup over the best classical approaches. A polynomial speedup is not as dramatic as the exponential advantage Shor's algorithm gives for factoring, but do not underestimate it. When the operation being accelerated is the dominant computational cost of one of the most expensive technologies humans have ever built, even polynomial improvement matters at scale. If quantum hardware matures enough to run HHL and related algorithms on real-world problem sizes, the cost and time needed to train and run AI systems could drop significantly. More speculatively, researchers are exploring quantum hardware inside neural network architectures themselves. The idea is called quantum neural networks. Instead of representing network weights as classical numbers, they may be represented as quantum amplitudes. Instead of classical activation functions creating nonlinearity, measurement of quantum states could play that role. Instead of classical matrix operations moving information forward through the network, quantum interference would do the work. In principle, a quantum neural network could represent and process certain kinds of high-dimensional data more efficiently than any classical architecture, because the Hilbert space it operates in is exponentially larger than a classical vector space of comparable physical size. But in practice, no one has yet convincingly demonstrated this advantage on a truly practical task. Current quantum hardware is still too noisy and too small. Many quantum neural network proposals that look promising on paper run into a problem called barren plateaus when training begins. The gradient of the loss function becomes exponentially flat. Training stalls. This is an active research problem. It is not obviously impossible to solve, but it means the path from theory to working quantum-enhanced AI is not as short as some hype suggests. The honest answer is this: quantum-accelerated AI is a real possibility. It is a genuine open question. It is not guaranteed, and it is not dismissed. But the connection between quantum computing and AI that may matter most is not only about algorithms. It is about something deeper, something related to what it means to understand a system rather than merely use it. To see that, think about what AI already is before quantum enters the picture. Large AI systems, the kind that generate text, analyze images, predict protein structures, and compose music, are already partly opaque to the people who build them. Their internal representations are high-dimensional structures. They encode relationships between concepts in spaces with thousands or tens of thousands of dimensions. The way those representations combine to produce a specific output is not something a human engineer can trace like a normal program. We can examine them from the outside. We can run interpretability experiments. We can identify patterns. We can sometimes find circuits inside the model that appear linked to particular behaviors. But we cannot simply read the reasoning. We cannot follow the logic step by step the way we can with code written intentionally by a programmer. The systems work. We do not fully understand why they work, and we use them anyway. Quantum computers add a second layer of opacity, and these two layers do not simply add together, they multiply. Computation inside a quantum processor happens in Hilbert space, a space far beyond what classical systems can describe. The interference patterns that create the output cannot be observed directly without destroying the computation. The intermediate states are inaccessible by definition. When you read the output of a quantum computation, you are seeing the result of a process that happened in a space you cannot inspect, following dynamics you cannot classically simulate. using correlations with no classical description. Now imagine a system where a classical AI, whose internal reasoning we cannot fully interpret, designs and optimizes quantum circuits. Those circuits run on quantum hardware whose internal operation we cannot simulate. An output comes out. It is useful. It may be the most valuable computation ever performed, but no human being anywhere can explain step by step how it got there. That is a black box inside a black box. There is a version of this that sounds acceptable. We use black boxes all the time. Your immune system is a black box. The global financial system is a black box. The weather is a black box. Black boxes produce useful outputs, and we learn to navigate around them. The point is not that black box systems are automatically dangerous. The point is that science depends on looking inside boxes. Science depends on mechanistic explanations. It depends on being able to predict behavior in genuinely new situations, not only interpolate from past examples. It depends on being able to say not just that something works, but why it works, and what it will do when conditions change in ways we have never seen before. A world where our most powerful computational tools are both quantum and AI, opaque from both directions, is a world where the gap between capability and understanding grows wider each year, and that may weaken the feedback loop that has historically driven progress. Technology improves science. Science improves technology. But if the tools become more powerful while the explanations become less accessible, that feedback loop begins to strain. Then there is an even stranger frontier. Researchers are beginning to discuss it carefully in technical papers and conference talks. The question is whether quantum AI systems may discover patterns in physical reality that are inaccessible to human-designed algorithms. Not because humans are not clever enough, not because classical computers are merely too slow, but because the patterns themselves live inside a space of quantum correlations that human intuition cannot navigate. Human intuition was shaped by evolution for a classical world. We track objects moving through space. We reason about causes coming before effects. We build mental models of systems we can observe. None of that mental equipment was built for a world where particles are entangled across hundreds or thousands of kilometers, where information has no clear location, where the substrate of computation may be distributed across parallel branches of reality. If quantum AI systems begin to operate effectively in that space, their outputs may not only be computationally opaque, they may be conceptually alien. We may receive answers we cannot understand, to questions we barely know how to ask. And as a civilization, we will have to decide what to do with answers like that. That may sound like the most speculative point in this entire story, but the hardware most likely to enable it is being built right now, not by Google, not by IBM, but by a team that has spent more than 2 decades pursuing a completely different solution to the stability problem. A solution that does not try to catch errors after they happen, but tries to make certain errors structurally impossible in the first place. And the physics behind that approach connects, in ways that are difficult to dismiss as coincidence, to everything we have been discussing about where quantum information actually lives. Part 13. Microsoft's topological qubit. Every quantum computing company on Earth is fighting the same war, and the enemy is reality itself. Quantum states are fragile in a way that has no classical comparison. A classical bit, a 1 or 0 stored inside a transistor, is relatively stable. You can warm it, you can vibrate it, you can shine light on it, and most of the time, it remains what it is supposed to be. The physical system settles back into its intended state because classical states are stable attractors. Push them slightly and they return. Quantum states are the opposite. They are less like a transistor and more like a soap bubble balanced on the tip of a needle. Any interaction with the surrounding environment can destroy them. A stray photon, a small vibration traveling through the mounting structure, an electromagnetic fluctuation from a cable a meter away, any of these can collapse the superposition. The quantum information disappears. The computation fails. Google and IBM have approached this problem like engineers approaching an extremely difficult engineering challenge. With precision, craftsmanship, and clever compensation systems, build the best superconducting qubits possible. Lower physical error rates using advanced materials, science, and circuit design. then place quantum error correction codes on top to detect and repair the errors that remain. It is a brute force strategy combined with elegant mathematics, and it is working. Sycamore and Willow prove that. Willow's below-threshold error correction, demonstrated in December 2024, is real progress on that path. No one should minimize it. But that path has a cost, and it is worth being honest about it. Quantum error correction requires redundancy. To protect one logical qubit, the qubit that actually performs the computation, you need many physical qubits. Those physical qubits must be spread across the hardware in a pattern that allows errors to be detected and corrected without directly measuring the protected logical state. Current estimates for fault-tolerant quantum computation suggest you may need somewhere between 1,000 and 10,000 physical qubits for one logical qubit. The exact number depends on the architecture and the target error rate. A quantum computer powerful enough to run Shor's algorithm against real-world encryption keys would likely require millions of physical qubits, maybe even tens of millions, all operating below the error threshold, all maintained simultaneously inside dilution refrigerators near 20 millikelvin. The engineering challenge grows with every qubit added. The path is real, but it is long. Microsoft has spent more than 2 decades betting there may be a shorter route. Their approach is not simply about better error correction. It is about building qubits that do not need error correction in the same way, because certain errors would be structurally unable to reach them. The approach is based on an exotic quasi-particle called a Majorana zero mode. To understand why that matters, you need to know a little about the man whose name it carries, because his story is one of the strangest in the history of physics. Ettore Majorana was an Italian theoretical physicist. He was considered a prodigy, even among a generation that included Enrico Fermi and Werner Heisenberg. In 1937, he published a paper proposing that certain quantum particles, specifically fermions with half-integer spin, could be their own antiparticles. Normally, every particle has an antiparticle with opposite charge. An electron has a positron. A proton has an antiproton. When a particle meets its antiparticle, they annihilate. Majorana proposed that some particles might be symmetric in a deeper way. They could be equal to their own mirror image, neither particle nor antiparticle in the usual sense, but something that is both at the same time. The mathematics was elegant. The physical implications were profound. Then, in March 1938, Majorana boarded a boat from Palermo to Naples. Other passengers reportedly saw him, and then he disappeared. He was never seen again. No body was found. No definitive explanation was ever established. He was only 31 years old. His physics survived. His fate remained a mystery. Majorana zero modes are not exactly the particles Majorana originally described. They are quasi-particles, collective excitations that emerge in certain condensed matter systems, especially in topological superconductors under specific conditions. They share with Majorana fermions the mathematical property of being their own conjugate. But what makes them powerful for quantum computing is something very specific. The quantum information they encode is stored non-locally. A Majorana zero mode cannot exist alone. It comes in pairs, and the two modes of the pair are spatially separated. The quantum information, the logical state of the qubit, is not stored in either mode individually. It is stored in the correlation between the two. It lives in the relationship, not inside either member of the pair. This is what Microsoft has been chasing for more than 20 years. And once you understand it, the reason is clear. If information is not located in one place, then local disturbances cannot easily destroy it. A vibration here cannot damage information that is not here. A stray photon there cannot flip a bit that is not there. To corrupt the information, you would need to disturb both separated modes at the same time in a correlated way. That requires a very specific type of noise. Random thermal fluctuations almost never produce it. So the qubit is not merely shielded from its environment, it is hidden from its environment. The information is stored in a way the environment is almost blind to. Physicists call this topological protection. The word topological refers to properties that are global rather than local. They describe the overall structure of something, not one tiny feature of it. Think about the difference between a sphere and a donut. A sphere has no hole. A donut has one hole. You can stretch, bend, or squeeze them. But unless you tear the object, you cannot turn a sphere into a donut, or a donut into a sphere. The number of holes is a topological property. It is globally defined, globally stable, and locally inaccessible. You cannot change it by poking one small part of the surface. You would have to change the whole structure. Topological qubits encode quantum information in a similar way. The logical state of the qubit is a topological property of the quantum system, not a local property. Local noise cannot access it because the information is not stored in any one local feature. It is stored in the global structure. The protection is not something applied from the outside. Not only a refrigerator keeping it cold, not only shielding blocking electromagnetic fields, not only an error correction code fixing mistakes after they occur. The protection is built into what the qubit is. You have not built something fragile and then defended it. You have built something whose structure itself is robust. In February 2025, Microsoft announced a chip called Majorana 1. They described it as the first demonstration of topological qubits reliable enough to serve as a computing platform. The physics community reacted with both excitement and caution. Both reactions were justified. Microsoft has worked on this approach for over 20 years. They have invested heavily, but they have also had earlier experimental claims in this area questioned and retracted. Most notably, a 2018 paper was formally corrected and eventually retracted in 2021 after problems in the data analysis were found. So the field has good reason to be careful. The 2025 announcement was more carefully documented. It passed initial peer review. It came with more detailed supporting evidence. But independent verification was still ongoing at the time of writing. The honest answer is this: it looks promising, but it is not yet confirmed to the standard the field requires, and the history of this research program suggests patience before celebration. But if it works, the implications change the entire timeline. A topological qubit may require far fewer physical components per logical qubit than superconducting approaches. Instead of thousands to one overhead, it might be closer to 10 to 1 or better. A processor with 1,000 topological qubits could, in principle, deliver the logical computational power of more than 1 million superconducting physical qubits. The path to useful fault-tolerant quantum computing would shorten by orders of magnitude. Hardware currently projected to require decades and millions of physical qubits might become achievable with thousands, possibly within years. But step back from the engineering for a moment, because the deeper point is philosophical, and it connects directly with everything else in this story. Topological qubits represent a different relationship between information and physics than almost anything humans have built before. In classical systems, information has a location. This electron is here. This magnetic domain points this way. This transistor is in this state. Information occupies a place in space. That assumption is so deeply built into our thinking that we barely notice it. But in topological quantum systems, information does not have a simple location. It is in the relationship between places. It is in the global structure. It is real. It is readable. It is usable. You can extract it. You can compute with it. But you cannot point to where it is. There is no single there. If you have followed this entire story carefully, that should sound familiar, because it is structurally similar to Deutsch's description of quantum computation across parallel branches of reality. In both cases, the information is real but non-local. In both cases, protection comes from global structure, not local features. In both cases, you can interact with the final output without directly observing the substrate. You get the answer, but you cannot watch it being computed. Whether that structural similarity is just formal, or whether it points to something deeper about where quantum information truly lives, remains an open question. But that question is becoming harder to ignore. The information is real. It has no simple location, and the machines that exploit it are becoming more powerful every year. Part 14. The simulation argument is no longer abstract. In 2003, an Oxford philosopher named Nick Bostrom published a paper that many scientists read, found interesting, and then quietly placed in the category of "not my department." The paper was titled, "Are You Living in a Computer Simulation?" It introduced what became known as the simulation trilemma. The argument was clean, logical, and deeply uncomfortable. One of three things must be true. Either nearly all civilizations capable of running detailed simulations of conscious beings destroy themselves before reaching that ability, or nearly all technologically mature civilizations simply have no interest in running such simulations. Or, if neither of those is true, simulated realities would vastly outnumber base reality, and in that case we are almost certainly living inside one right now. The mathematics is straightforward probability. If simulations are possible and civilizations run them, then simulated minds would vastly outnumber non-simulated minds. And statistically, you would probably be one of the simulated ones. The argument became famous. It made for excellent late-night conversations. But for most working scientists, it stayed comfortably in philosophy. An interesting thought experiment about possibility, not a scientific hypothesis about reality. There was no direct experiment to run, no clear prediction to test, no obvious way to falsify it. So for 2 decades, it remained fascinating but inert. Then quantum computing changed the conversation, not in the way most people expected. Quantum computing does not make the simulation argument easier to dismiss. It makes it harder, not because it simply brings us closer to building simulated realities ourselves, though that is also an interesting question, but because it changes what we understand about the physical requirements for simulating a universe like ours. And what it reveals is this: simulating quantum reality is not just harder than simulating classical reality, it is incomparably harder. The difference is not only degree, it is kind. Richard Feynman made this point in a 1982 lecture that helped inspire quantum computing itself. He observed that simulating the time evolution of a quantum system with n particles on a classical computer requires resources that grow exponentially with n. Every particle you add roughly doubles the computational cost. A system of 300 particles requires a classical state space larger than the number of atoms in the observable universe. You cannot do it. Not by adding more processors, not by adding more memory, not by waiting longer. The mathematics simply does not allow efficient classical simulation of quantum mechanics. You cannot efficiently simulate quantum mechanics on a classical computer because the quantum state space is too large to fit inside any classical physical system. This is the same exponential scaling problem we have already seen from the other side. Quantum computers access exponentially large state spaces precisely because they are quantum. Classical computers cannot simulate them efficiently for exactly the same reason. These two facts are mirror images, and together they lead to a very uncomfortable implication. Here it is plainly. If our universe contains genuine quantum mechanics, not just statistical uncertainty, not just a useful mathematical shortcut, but real superposition and real entanglement, the kind confirmed by Bell experiments and demonstrated by the MISSIS satellite over 200 kilometers of open sky, then any computational substrate simulating our universe would need to be quantum, or it would need something equivalent to quantum capability. A classical computer, no matter how large or fast, could not efficiently simulate quantum reality. It could not fake entanglement. It could not reproduce Bell inequality violating correlations using a local deterministic computation underneath. If we are inside a simulation, the simulator is not classical. The simulator is quantum. And this is where things become genuinely strange. Decades of Bell experiments, ending with loophole-free tests in 2015 and honored by the Nobel Prize in 2022, have shown that our universe does not have local hidden variables. There is no classical layer beneath quantum behavior, no deeper deterministic machinery that simply looks random and non-local from our point of view. Any simulation producing the quantum statistics we observe must genuinely instantiate quantum processes. It cannot fake them with something classically simpler underneath. Physics rules that out. So if simulation exists, it is not running quantum mechanics as a clever illusion on top of classical mechanics. It is doing quantum mechanics all the way down, with no shortcut. Now combine that with the earlier discussion about quantum computation and parallel universes. In David Deutsch's framework, quantum computation works because processing is distributed across parallel branches of reality. The resources that make quantum computation possible are not contained in any single branch of any single universe. They are spread across the wave function. If that framework is correct, and machines like Willow look disturbingly consistent with it, then a quantum simulator powerful enough to run our universe would itself require resources from parallel branches of reality. You cannot have a quantum simulation without a quantum simulator. And a quantum simulator is not simpler or more ordinary than the universe it simulates. In some frameworks, it is the same kind of thing described from another level. The mystery does not disappear when you move one level up. It reappears at that level. Think about what that does to the original simulation argument. Bostrom's version assumes a clear hierarchy. There is base reality, and there is simulated reality. The simulator is more fundamental. The simulated world is the copy. The simulator stands outside and runs the program. That hierarchy is what gives the argument its emotional weight. If we are simulated, we seem less real, less fundamental, contained inside something else that is more real. But quantum mechanics weakens that hierarchy. If the simulator must be quantum, and if quantum computation requires multiverse-level resources, then the simulator must itself be embedded in something as vast and strange as a multiverse. The simulator is not standing outside reality running a simple program. In every physically meaningful way, it is caught inside the same quantum strangeness we are. The clean boundary between real and simulated begins to look less solid, maybe even meaningless. There is another constraint that makes this more striking. If we are in a simulation, Bell experiments tell us that the simulation cannot take shortcuts with quantum correlations. Every entangled pair of particles in every laboratory experiment must maintain correlations that cannot be generated by local classical computation. There is no cheaper way to produce these correlations. The simulation would need to maintain genuine non-local quantum correlations across the entire observable universe, across space, across time, in real time, without loopholes, because the loopholes have been tested, and the loopholes are gone. That is not a modest computational requirement. That is an extraordinary one. Either the simulator controls resources that make our observable universe look tiny, or the distinction between simulator and simulated has broken down. And what we call the simulation and what we call the simulator are, in the deepest physical sense, the same type of thing. Bostrom's argument often assumes simulated reality is less real than base reality. Quantum mechanics suggests that assumption may not hold. Whatever structure generates the quantum correlations we observe, whether we call it the universal wave function, the multiverse, the information substrate, the simulator, or something we do not yet have a name for, that structure is not simpler, more familiar, or more classical than the universe it produces. It is at least as strange, and the evidence suggests it may be stranger. We have not found a familiar foundation beneath the weirdness. Every time we search for one, we find deeper weirdness instead. And here is the part that stays with me when I think about this carefully. By building quantum computers, we may have accidentally created instruments that push against this boundary, not from outside the simulation, from inside it. If we are simulated, then we are building devices inside the simulation that appear to access the computational substrate of the simulation itself. Devices that draw on resources no single classical branch of reality can provide. Devices whose outputs, if the physics is taken seriously, require either a multiverse or a simulator that is itself multiverse-like. Science cannot yet answer whether we are in a simulation. Maybe it never will. But whether we have built devices capable of probing the structure beneath reality, that question is beginning to look much less rhetorical than it did 10 years ago. The machines are running, the outputs are real, and whatever they touch when they compute is not nothing. Part 15. The quiet possibility no one wants to say. Now let us bring all the threads together. Not to fully resolve them, they do not resolve. Not yet, maybe not ever, but to place them side by side and see the shape they form. We started with a machine. Sycamore completed a calculation in 200 seconds that would take classical hardware thousands of years. Willow showed that adding more qubits can stabilize a computation instead of destabilizing it. That violates almost every engineering intuition we have built across centuries of working with complex systems. These are not just interpretations. They are not just theories. They are experimental results, published, peer-reviewed, reproducible. We followed the mathematics to its conclusion. A modest quantum computer of 300 qubits would simultaneously occupy more states than there are atoms in the observable universe. The information being processed cannot be stored in any physical substrate inside a single instance of reality. That is not an engineering limit, it is arithmetic. The numbers do not fit. We met David Deutsch. In 1985, he made this argument formally and concluded that quantum computation requires the resources of parallel universes. We met Hugh Everett. 30 years earlier, he had created the physical framework Deutsch was drawing from. The many-worlds interpretation, a picture where the wave function never collapses. All outcomes are real. And reality branches, both were largely ignored for years. But the quantum hardware being built now fits their predictions better than many alternatives. We watched the Nobel Committee honor the experimentalists who showed that local hidden variable theories are wrong. There is no classical reality beneath the quantum one, no hidden variables quietly carrying pre-existing answers. At its most fundamental level, the universe is not local and classical in the way Einstein hoped. The correlations between entangled particles are real, non-local, and not mediated by any classical mechanism. We watched a satellite maintain quantum entanglement across 1,200 kilometers of atmosphere. That confirmed entanglement is not just a delicate laboratory trick. It is a global phenomenon, one that operates at scales relevant to real infrastructure. We encountered the ER-Hansa-EPR conjecture, the idea that entanglement and geometry may be two descriptions of the same thing, that space itself may emerge from quantum connections, and that a quantum computer may be constructing and navigating the geometry of a deeper space beneath the one we observe. We met John Wheeler. We followed his it from bit idea to Landauer's principle. We saw experimental confirmation that erasing information has a physical cost. Information is not just abstract. Information is physical. The substrate of reality may be informational rather than material. From there, we moved to the holographic principle, the suggestion that the three-dimensional world we experience may be a projection of information encoded on a two-dimensional boundary. Then we came back to Earth. We saw that governments and financial institutions are already preparing for a post-quantum world. Encryption standards are being replaced. Future data is being protected from machines that do not yet exist. Because the people who understand this field best believe the threat is real enough to act now. We saw quantum hardware converging with artificial intelligence, a combination that may create systems doubly opaque to human understanding. AI systems we cannot fully interpret, designing quantum circuits we cannot fully simulate, a black box inside a black box. We saw Microsoft's bet on topological qubits, qubits that protect information by encoding it in non-local geometric structure rather than any local physical property. Then we arrived at the simulation argument, and we found that quantum mechanics makes it harder to dismiss, not because it proves we are in a simulation, but because it shows that any substrate capable of generating our universe must itself be doing something as strange and non-classical as quantum mechanics. So what do all these threads have in common? They all point toward the same possibility from different directions, using different tools, different experiments, different languages. The possibility that reality, at its deepest level, is not what classical physics told us it was. It is not merely a collection of local, definite objects moving through space according to fixed rules. It is something stranger, something whose full description requires a mathematical space larger than the observable universe, something that maintains non-local correlations without classical signals, something that produces computation no single physical instance of matter can host. So what are the options? There are basically three. The first option is that quantum mechanics, as we currently understand it, is incomplete. Maybe there is a deeper, hidden layer of physics we have not discovered yet, a layer that explains all the non-classical behavior in a classical way. Maybe the exponential state space is just a feature of the mathematics, not a description of physical reality. Maybe entanglement is real, but will eventually be explained by a local mechanism we have not found. This is the option Einstein preferred. But Bell's theorem and later experiments have made it extremely hard to defend. Loophole-free Bell tests have been performed. The experimental exits from local realism are closed. This option requires a replacement theory that preserves every successful prediction of quantum mechanics while having a completely different underlying structure. So far, no one has built such a theory. The second option is that quantum mechanics is correct and complete, and that what it describes is genuinely non-classical. Superposition is real. Entanglement is real. The exponential state space is real. Quantum computation genuinely accesses resources that no classical physical system in one universe can provide. Deutsch and Everett were right in the most important sense. The wave function branches, the branches are real. Quantum computation works because it is distributed across them. This is the option the evidence most directly supports when taken at face value. It is also the most philosophically disorienting because it means most of reality is permanently inaccessible to us. The vast majority of quantum branches run parallel to us with no possible interaction, and we are, at every moment, only one branch among an unimaginable number of others. The third option is that something new is missing, a framework we do not yet have, a physics that is neither classical nor quantum in the current sense, something that solves the measurement problem, explains entanglement, accounts for the computational resources, and clearly tells us what is actually happening when a quantum computer runs. This is probably the option many working physicists would prefer. It would be science doing what science often does. When existing frameworks break down, build a better one. But right now, there is no candidate theory that commands consensus. No framework most physicists agree has solved the problem. The measurement problem is decades old, and it is not clearly closer to resolution than when it was first named. Interpretations multiply. Consensus does not. The honest answer, the one that requires courage to say clearly, is this. We have built machines whose operation we cannot fully explain. We can describe them. We can operate them. We can program them. We can read their outputs, but we cannot fully describe the physical substrate where their computation occurs. The remaining options all require something enormous. Either we must revise our picture of reality in ways we have not yet achieved, or we must accept that reality is far stranger than any previous generation of humans was forced to confront. And there is something strange and almost beautiful about that. Every generation believes it lives at the edge of human knowledge. Most generations are partly wrong. Many mysteries eventually get ordinary explanations, but sometimes humanity really does stand in front of something that does not fit, something that refuses to be reduced to familiar terms, something that demands to be understood on its own terms or not understood at all. Quantum mechanics has been that thing since 1927. Quantum computing has made it impossible to leave the deepest questions for future theorists, because the machines are here now, they are running now, they are producing results now. Results that exceed the physical resources of the observable universe. They exploit correlations that are non-local, robust, and still not fully explained. They demonstrate stability that seems like it should not exist. They perform computations classical systems cannot simulate, and they are improving every year. You may find this frightening, and there is a version of it that is frightening. The most powerful computing technology ever built may be operating on principles we do not fully understand. Using resources we cannot clearly identify, inside a physical substrate we cannot directly observe. That is a reasonable thing to find unsettling. The power is real even if the explanation remains incomplete. The consequences for encryption, AI, science, and our picture of reality are real, even if interpretations remain contested. But there is another way to hold the same facts, not with fear, but with the kind of wonder that comes from standing at the real edge of knowledge. Every piece of evidence in this story points toward the same conclusion. We have built something that accesses a level of reality our best physics says is real but cannot fully describe. We have built a tool that is in some sense larger than the universe it operates inside. We built it without fully knowing what we were building. We built it before understanding where its power came from, and it works. There is a long tradition in science where tools outrun theories. Humans used fire for hundreds of thousands of years before understanding combustion. We built bridges for millennia before modern structural engineering. We used anesthesia before fully understanding neuroscience. In each case, practical ability came before complete theory, and eventually theory followed, changed by the existence of something that should not have worked but did. Quantum computers may be that kind of thing. We built them, they run, but we do not know with confidence, consensus, or one complete framework why they run. We do not know exactly where the computation happens. We do not know what physical reality is hosting the information. We do not know whether parallel branches are real, or whether the information layer is primary, or whether space-time emerges from entanglement, or whether we have built the first device that directly probes the structure of a simulation. What we know is that the machine works, and the question of why it works, the real why, remains open. Not only theoretically open, experimentally open. Right now, experiments are being designed in laboratories across the United States, China, Europe, and elsewhere. Experiments probing the relationship between entanglement and space-time geometry, testing predictions from candidate theories of quantum gravity, searching for evidence of the informational structure Wheeler sensed decades ago. The answer is not here yet, but the question has never been more precise. And the machines asking that question are becoming more powerful every year. As a species, we are standing at a very specific and historically unusual moment. We have built a device that our best theories suggest should not be possible inside a single universe. We have experimentally confirmed that many of the assumptions needed to dismiss that conclusion are wrong. And we may have accidentally built the first instrument in history capable of probing the structure of reality where classical physics ends and something stranger begins. We did not set out to do this. We set out to build a faster computer. We succeeded, but we also opened a window into something that does not yet have a name. No agreed interpretation, no comfortable explanation. Inside refrigerators colder than the space between galaxies, computations are running across more states than there are atoms in the observable universe. This is happening right now. The machines are running. The outputs are real. We simply do not know where the computation is happening, and that question, honestly faced with all of its implications, may be the most important open question in science, not only because of what the answer could do for technology, though it will do a great deal, but because the answer, when it finally comes, will tell us what reality is. Not what it is made of in a shallow chemical sense, but what it fundamentally is, what kind of thing exists, how many branches there are, whether space is built from quantum connections, whether information is the ground floor of being, whether the universe is, in the deepest possible sense, a computation. The machine works, we just do not know where.